with atomic physics. So probably even some college classes may not cover this information, but the bulk of it, a little bit requires calculus, but what I'm going to do, what I have done, what I'm going to provide for you is this whole handout. And it's several pages up front dealing with things, and then my own handwritten notes of about 5 pages, handwritten notes of derivations. And then the actual questions are on page 10 and 11 and 12. And the questions are not that difficult questions as long as you understand kind of the overview of what we're talking about. Basically, what we're talking about is what we're going to do is to go over the history of how the hydrogen spectra came to be analyzed first. If we take a bulb and put hydrogen gas in here, okay, and then we put an electrode in here, and we excite this with electricity. With the hydrogen gas gets what we say excited. It goes to high energy levels and it decays back down, and it gives off hydrogen light, or light coming from the hydrogen, the hydrogen gas. Okay, we get hydrogen gas. So, and what we see is the hydrogen gas. If we look at the light, just like we're looking at the light here, and we run it through a spectrometer. Spectrometer is a device where we take the light. It's basically a prism, a very calibrated prism, where the light comes in, it refracts, and it refracts into the various colors. Okay, and then we put a plate over here, and this is all put in a very detailed box and with the angles. Anyway, if we take this hydrogen light, the hydrogen spectra, what's called. Spectra is short for spectrum, okay, or spectrum. And we take it through a prism and we separate the colors. What we find, it's not like white light at all. What we get is we get distinct bands of light. And the bands of light are very sharp geometric pattern. They space out really. At this point, they all jumble up, and then as you get and this is short wavelength to long wavelength, they get longer and longer, and the spacing gets real long out here. Okay, so the question is, when the early researchers found this, they had no explanation for it. And so this is around the time of the late 1800s that scientists were starting to do this. And so actually, around the mid 1800s actually. And first you had this man called Johann Balmer. Now Balmer, turns out, he was in Germany. He was basically a high school student. Excuse me. He was a high school teacher. And he was a high school teacher, and he taught mathematics, but his favorite thing to do was to play with numbers. And somebody told him he liked to just play games with numbers and sequences of numbers. He wasn't really a physicist at all, which is an amazing thing. Someone gave him these wavelengths, and they said, here's a series of numbers that no physicist can really understand. And it seems like there's a pattern to it, but nobody can figure it out. Well, Balmer, in 1885, he was very good with working just with raw numbers and looking at patterns in numbers, and he came up with a formula. And the formula was this, that the wavelength is equal to hm squared over m squared minus n squared. Okay, and this constant here, h, was a constant. It was equal to 3 64.56 nanometers. Okay, and this is not Planck's constant. It's just some other constant, arbitrary constant he came up with. And m, in his case, n equals 2, and m equals 3, 4, 5, 6, dot, dot, dot. So these are integers. And if you plug this in, sure enough, it basically predicts where the next wavelength is going to be. Okay? So, so this was said they called, in honor of his work, they called this, and he was just basically a high school mathematics teacher. He wasn't really a physicist at all, but they called this the Balmer series in honor of him. Well, so he came up with a formula, but no one knew why this formula worked. It works, but no one really understood it. Okay, Rydberg in 1888 and a physicist named Rydberg, he took the Balmer equation and he generalized it. By the way, that was page 2 of the handout. Now I'm flipping over to page 3 of the handout. Balmer took this and he basically reworked the Balmer equation just a little bit, and he came up with something that looked a little, it's just essentially the same thing but in a different form. 1 minus n1 squared minus 1 minus n2. Okay, where n1 and n2 now replace m and n. So instead of having m and n be integers, now the integers are simply n1 and n2. And if, for instance, if we have the Balmer series, n1 would be 2, and n2 would be 3, 4, 5, 6, etc. Okay? So, now it turns out when you have n1 equals 2, there's a whole series of these lines. When n1 equals 1, we had what's called the Lyman series of lines, at the hydrogen lines. When n2 equals 2, that was the Balmer series, and etc. There are different series that different physicists actually observed in the laboratory. Well, and this RH was a constant. We just call it the Rydberg constant, and that equals 1096778, and it's 1 over meters. Okay, so it's a very big number, and again, this is a constant. Well, again, no one really understood what was going on, but what I'm going to do is now look on the page, on top of page 4. What we're going to do is we're going to just jump to what's actually going on in the hydrogen atom. Again, you remember the hydrogen atom, we have a proton in the nucleus, and we have one electron that spirals around. Okay, and we know now that basically the electron can fly at different orbits. So we have what's called the ground state, and if the electron gets energized, it kicks up to a higher energy state, and then when it comes back down, it gives off a photon. Okay, it gives off a photon of light with a certain frequency or certain wavelength. And remember that the frequency times a wavelength equals to the speed of light. Okay, so basically we now know that And this is all under the realm of atomic physics. Atomic physics being the study of the orbits of the electron around the nucleus. That's atomic physics. Whereas nuclear physics is dealing with the nucleus of the atom. Okay. So we talk about atomic physics, where we studied the spectra, the light spectra, dealing with the electron orbit, and nuclear physics, where we talk about the nuclear spectra. Actually, the nucleus can give off spectra like gamma rays and things like that, dealing with the protons and neutrons in the middle of the nucleus. So if you're taking a course in physics, all of what we're going over now would be covered kind of under the general heading of atomic physics. So what we have here is, and if you look on top of page 4, basically the energy level of the electron, this will be the ground state. The next highest state, this would be state number 1, 2, the next highest state is 3, and then as you go to subsequent states, the levels get closer and closer together. Okay, where way out here, up at the very top, they basically form a continuum. Okay, so if you have an electron here in the ground state, if we energize it, it can then fall back down. So if we have, suppose we have an electron that jumps from here to here. If the end orbit, if the end level, see this is basically the way this works, is N1 is our stop level, and N2 is our start level. Now this equation begins to make sense. If we're at this is level, if we start from N2 and jump down here to N1, this would be N2 would be 2 and N1 would be 1. Okay. So if we start here, and that would give off a certain size photon. This energy level, basically the energy comes out in an energy photon. Okay. Well, I'm getting a little bit ahead of myself, but we're going to tie this in to Niels Bohr at this point. Niels Bohr, all this for a couple decades, no one really understood this until Niels Bohr came along. In 1912, Niels Bohr was working with this, and the interesting story about this is that Niels Bohr he was a European physicist, and he was a young man in his 20s. He had just gotten married, but he was really hot on the trail of understanding all of this atomic hydrogen spectra. He was really, really close, but he wasn't quite there yet. But he just got married, and the story is that he told his wife, sorry, we're going to have to postpone the honeymoon because physics comes first, basically. So, and he had to get back and really kind of nail the mathematics of this down. So I guess his wife understood. So anyway, but he did. He went to work, and what we flip over to page 5, and okay, basically the way this works is the energy. Remember Planck's law. Energy equals h times f, where this is Planck's constant. That the energy, and remember this energy level, and this is the energy of the photon. So in other words, if an electron jumps to ground, to state number 2, and then it decays back down, this energy level, the energy from here to here, this energy difference, gets translated into a photon whose frequency is f, and whose wavelength, if we remember, f lambda equals c, therefore F equals c over lambda, so we can say it's also h c over lambda. Okay, so that when a photon, when an electron decays from this orbit down to the ground orbit, it gives off a certain amount of energy. That energy, through this equation, comes out as a photon of light at a certain wavelength or frequency. Typically, we deal with the wavelength because the frequency is so high. So it turns out, and what, so if we notice that if the electron started up here, the energy given off would come from here all the way down to here. So here we'd have the start level as 3, and the stop level is 1. Okay. So now if we had the Balmer series, in the Balmer series the stop level is 2. So basically what that would mean in the Balmer series, the start level is 3, but the stop level is 2. Or the start level is 4, the stop level is 2. So this level exchanges in energies of this sort, where the stop level is 2. This is what we call the Balmer series, where n1 equals 2. And notice, if n1 is 2, then all the other, the n3s have to be greater than that. So now we can start to understand why this equation makes sense, okay, from this point of view. Now, and we say that the energy is quantized, and in fact it is quantized, but how did, the question is how did Bohr come up with this? He came about it, it's simple for us to see it now, or we think it's simple for us to see, but actually for the physicists back in the early 1900s, it was difficult to see. They didn't know what we know now. They were coming up with the stuff. What I'm going to show you over the next 5 pages, real briefly, is how Niels Bohr, even came up with this theory. The first thing, we think of the energy as being quantized, but it's not quantized really the way you think it's quantized. What's really quantized is the angular momentum of the electron. So it's not just and that's what we're going to and this is we're going to talk about this, and this is the thing that Niels Bohr struggled with for a while. Okay. First of all, I'm going to erase this here, and we're going to start just with this equation here, and this is exactly how Niels Bohr started. He started with the, what did Niels Bohr have? He had Planck's law, he had this equation, he knew this, and he knew the Rydberg equation. But that's basically all he knew. There was a lot he didn't know. So, first of all, he took this equation, and he did something like this. Okay. And I'm on the bottom of page 5 here. Okay, now he took this and he solved for 1 over lambda. And if I I'm going to divide by hc, so I get E over hc equals 1 over lambda. Now, and he had an idea of these orbits. So what we want to say, here's a nucleus, and he imagined that we had the energy of the lower level and the energy of the upper level. And he thought, okay, well, we have an electron here, and the electron goes from the upper level to the lower level. And so the energy difference here is the energy of the upper level minus the energy of the lower level. Okay, he started with that, and so he's going to say 1 over hc times the energy of the upper level minus the energy of the lower. I'm just going to abbreviate them, U for upper, L for lower, 1 over lambda. And he said, okay, well that must equal somehow this. This is the Rydberg formula, which he had. This had already been derived about 2 or 3 decades before, so he knew that. Okay, so that takes us down to the bottom of page 5. So this basically is how Niels Bohr started. Okay, now what did he do? Now we go to page 6, and what he did is he used, and this is where the calculus comes in. And again, I'm just going to go over this very briefly. But if you have a hydrogen atom, okay, how do we calculate the kinetic energy of this hydrogen atom? We know that the Coulomb force is equal to mass times with the Coulomb force is equal to the centripetal acceleration. So this is exactly what Niels Bohr did. The Coulomb force is simply K. Now in place of the proton, what I'm going to do, the proton has a charge of, we're going to say plus E, and the electron has a charge of minus E. We ignore the signs for not right now, so the two charges become E times E, or E squared. Okay, so E is the charge of the electron. There's also the same charge of the proton. Okay. And this is equal to mass, the mass of the electron, times the velocity squared over r. That's the force. This we've seen before. Okay. We're going to divide by r. Okay. Now I'm going to calculate, so we have that, let me erase this. Basically we have K E squared over R equals mv squared. Well, if I want the kinetic energy, what is the kinetic energy? The kinetic energy of the electron is simply 1/2 mv squared, so I simply have to multiply this by half. So I'm going to put 2. So we have that the kinetic energy of the electron is K E squared over 2R. Okay? In this case, so that's the kinetic energy. Now what he did is he said, well, now I want to calculate the potential energy. Okay, and basically, to calculate the potential energy, what we do, well, and let me say, where are we going with this? What we want is we want the total energy of the electron. The total energy of the electron is the kinetic energy plus the potential energy. So that's where we're going. So we have the kinetic energy of the electron. Now we want to calculate the potential energy of the electron. And what we do is we look at what is the energy required to take that electron and move it all the way out to infinity. Okay, so basically we want to take this electron that is at a certain radius, but now we want to move it all the way to the radius is out at infinity. That would remove it completely, and we can figure out what that energy is. Because that, now remember, potential energy is the energy, the one way to calculate the potential energy would be to say what would be the energy that's required to bring that electron all the way from infinity out to this point here. Okay, so we start with work is equal to force times radius, or distance. We do a little bit of incremental work is equal to that force times a little bit of r. And so the total work or the total potential energy, is where we integrate this, we integrate that force over r, and then we take it from limits of r equals infinity to r. Here's where the calculus comes in. And the force here is simply the Coulomb's force. K E squared over r squared dr. And we integrate this, and I'm just going to write it. But basically, if you haven't had calculus, it comes out to be, the equation comes out, this is the same thing as potential energy. And it comes out to be, the equation is minus K E squared over R. Okay? So, and that's the energy it takes to bring an electron from way out here out to this point here. Why is it minus? It's minus because the electron, remember the electron is attracted to the proton, so it wants to come in. So you basically have to hold the electron back with a certain amount of energy because it's wanting to fly into the nucleus. Okay? So so here's the equation. So we now have the equation for potential energy. Potential energy of the same electron is minus K E squared over R. Well, let's add those two together. We add those two together, and the total energy is minus K E squared over 2R, if you add them together. Okay, so that's the total energy of the of the electron. That is the kinetic energy plus the potential. Okay, now what Bohr did is he took. Now remember, we're at the top of page 7 here, and okay, what Bohr did is he had these equations, and he also had, I'm going to write it backwards here. I'm using the Balmer series here. He noticed that these two equations were very similar, both in terms, the right-hand side of both is 1 over lambda, 1 over the wavelength, and he derived this, the difference of the upper energy and the lower energy, and he had this from the Balmer series, using the Balmer series as an example, and so he thought, well, these two must be linked. So somehow this must be related to this. And so he took the total energy and he stuffed it into here. And when you do, when you take this and you stuff that into here, and I'm going to flip up to page 8, what you end up with is 1 over hc times minus Ke squared over 2 times 1 over Ru minus 1 over Rl equals 1 over lambda. Okay? So he got the equation down to the form of the upper radius and the lower radius. Okay? At this point, he considered angular momentum. Here we're in the middle of page 8. You're at the middle of page 8. Now remember, angular momentum is L is angular momentum mvr. And remember that if we have the angular momentum of the electron around the nucleus. So if we have F equal ma, again, and again, this is the Coulomb's law, so this is Ke squared over R squared equals mv squared over R. Okay, we start with that, and now we're going to substitute, mvr, we're going to substitute the fact that we can take, if we take this, L squared equals m squared v squared r squared. And so basically we're going to substitute this into here, and we get, well, here, let's do it over here. L squared, we're going to solve for v squared, divided by m squared r squared equals v squared. Now we divide by r. Well, no, we're just going to substitute this directly into here, and we end up with m over r times L squared over m squared r squared equals k e squared over r squared. Okay, so let's figure this out. Let's cancel some terms here, and the r squared here cancels out. One of these m's cancels out, and we're left with, let's solve for 1 over r is equal to